All right, so let's look at the energy of a pendulum first. It's pretty much the easiest one to start with. So if we've got a pendulum here, sitting there, equilibrium, and we drag it back over here, okay, what kind of energy, or does this pendulum have any energy? The first day I hooked the mass to the string and drug it back in the room, and I asked you what has changed. A lot of you gave me a nice choral response of what? The potential energy. So there is gravitational potential energy in the spring, in this pendulum, pardon me, there now. Okay, I let it go, and as it goes through the lowest point, okay, lowest point where y equals 0, so then what's the energy? It's all kinetic energy. Very good. Okay. Okay, so if we just look at the maximum displacement and the minimum displacement, we could, and if we assume that there's very low friction in the system, how could we write, or how could we relate these two energies? They're equal to each other. And there's some special physicsy thing that tells us that they should be equal to it. Conservation of energy, that's right. So by the conservation of energy, we should get that the maximum gravitational potential energy would be equal to the kinetic energy if we're looking at this position, the maximum position and the minimum position. What was the equation for gravitational potential energy? It is mgy, and kinetic energy, 1/2 mv squared. Okay, so what doesn't matter? Still, mass doesn't matter. Okay, bam, we'll just get rid of mass. So, gy should equal 1/2 v squared if this is true. So let's do an experiment where we can test this. Now, do I know what the acceleration due to gravity is? Yeah, and because we're going to do a little experiment, let's use the acceleration due to gravity as it should be, 9.81. That'll give us the best answer. And let's have our pendulum start at a very low height just to keep everything nice and safe. But let's start with 1 centimeter. So would that be 0.01 equals 1/2 v squared. Okay, so I can manipulate the height, and we know the acceleration due to gravity. But if I'm actually going to let this thing go, how am I going to get the velocity? So yeah, I can use a probe, and we're going to set up to find the velocity as it passes through the photo gate. So let's do that now. All right, so this perfect answer should be that our velocity was what, 0.44 meters per second? And when we experimented, we found our experimental velocity to be about 0.46 meters per second. So we decided that it was pretty close to being a conservation of energy, with the idea that there could be some error involved in releasing it or marking the exact height. It wasn't, measuring was pretty difficult, and releasing was difficult. We could improve this lab by doing what? Any ideas? Yes, if there was like a robot that could let go of it, or something that would let go of it instead of, yes, then there would be robot error. And maybe even if we had a better measuring tool instead of just a meter stick. Okay, so with your group at your table, there should be a whiteboard near you. Anything can be erased. I'd like for you to draw a graph of the kinetic energy of our pendulum versus time, a potential energy of the pendulum versus time, and a total energy of the pendulum versus time. But I want you to only do this for 1/2 of a period. 1/2 of the period. All right, so initially the kinetic energy was 0. So I like the graphs that I saw that had an initial kinetic energy of 0. Then it has a maximum kinetic energy as it passes through the lowest point of the swing. And then when it's at the highest point of the swing, halfway through a period, it's back to 0 kinetic energy. And initially there's a very high potential energy. It goes to 0 potential energy with reference to the lowest point of the swing, back up here. And then energy, total energy, is constant. So very good. All right, so let's look at a little